Okay, start the presentation. So thanks for coming. So my thesis work is on efficient resource allocation for underlay D2D networks with limited channel state information.
Make it full screen.
So let me start by with the motivation for D2D communication. In device-to-device D2D communication, the devices communicate directly with one another. So it is unlike the conventional cellular communication, where two users communicate through uplink and downlink via the base station. So because of the direct communication, we can offload traffic from the base station, and since only one hop is involved instead of two hops, we can save on transmit power, which can increase the energy efficiency, and we can also save on the end-to-end transmission delay latency. We also see that the D2D communication reuses the frequency, reuses frequency, which can improve the spectral efficiency. So some of the applications of D2D communication are vehicle-to-vehicle networks in which the vehicles interact with one another using D2D communication.
This is the point.
And the other application is content distribution networks, wherein content such as video is distributed within a local network using D2D communication. So D2D can also be used as a relay to reach out to the to connect to the user that is not in the cellular coverage. So there are many other applications such as gaming and local advertisement and first responder communication networks and so on for D2D communications. So we focus on underlay D2D, wherein the cellular users and the D2D users. Yeah. The cellular users and the D2D users share frequency subchannels. Yes, this increases the frequency reuse. However, it also causes interference to one another. The cellular users cause interference to the D2D users, and the D2D users cause interference to the cellular links. This decreases the SINR, which consequently decreases the transmission rate of the users. So to manage the interference between the users, resource allocation is the key. So what do we mean by resource allocation? So resource allocation determines the transmit power, the power with which the users transmit with, and at what rate they transmit with, and also on what subchannels they transmit with. We focus on subchannel allocation of the D2D, on subchannel allocation part of the D2D pay in the resource allocation. So we will see that for resource allocation, the CSI acquisition is very critical, because for efficient subchannel allocation, the SINR or the rate of the D2D base is required, and the SINR depends on the channel gains of the links in the system. So if we look at the links in the underlay D2D system, there are many links in the system. So we categorize them as the direct links and the cross links. The ones in the blue are the direct links, the cellular user to base station links, the D2D transmitter to base station links, and the these are the direct links because they are directly connected to the base station. And the ones that are not directly connected to the base station are the cross links that are shown in red. The D2D transmitter to D2D receiver, the cellular user to D2D receiver, and the interference links between the D2D pairs are the cross links. If we have n cellular users and n subchannels and m D2D pairs, so there will be m times n D2D transmitter to D2D receiver links. There will be mn CU-to-DRx links. There will be m choose 2 times n the inter D2D interference links. So acquiring the CSI of these links is difficult because it needs cooperation and synchronization between all these users. And moreover, feeding back the CSI of these links to the base station will cause significant feedback overhead. In fact, the feedback overhead is of the order of nm square. The feedback overhead increases quadratically with the number of D2D pairs n. So in our thesis, we address the resource allocation in underlay D2D and the associated CSI issues. Our contributions in the thesis are as follows. We propose two CSI models that has low feedback overhead. We consider subchannel allocation that has a limit on the number of D2D pairs that can share a subchannel. For that to address that subchannel allocation problem, we propose two algorithms. One is CCSAA, that is based on submodular maximization based approach. The other one is RPA relaxation pruning algorithm that is based on LP relaxation and rounding based approach. And so we also investigate an interesting interplay between the two CSI models that we propose and the two algorithms. Finally, we will see the disjunctivity, we'll see subchannel allocation problem based on disjunctivity constraint. And to address that, we use branch and bound algorithm. Let's start with partial CSI model. The first one in the two CSI models is the partial CSI model. In this model, the base station knows the channel gains of the CU-to-D base station link and the D2D transmitter to base station link. Because these are directly connected to it, it can estimate this instantaneous CSI of these links using the pilot signals. However, the DRx, the D2D receiver, knows the instantaneous CSI of the D2D transmitter to receiver link, the CU-to-DRx link, but it only knows the statistics of the inter-D2D interference link, the interference from the other D2D users, and the intercell interference from the stats of intercell interference from the neighboring cell users. Using the CSA available to the D2D receiver, it computes the SINR and it computes its D2D SINR. So how does it compute? So the D2D SINR is computed as follows. It computes the D2D SINR, the SINR for D2D pair J and subchannel I is shown here. So wherein we have the D2D transmitter to receiver link gain, and the interference in the denominator, we have interference from the cellular user, and this is the inter D2D interference from the other D2D users and the intercell interference. So we know the CSA of this link and this link, the instantaneous CSA of this link and this link, but we only know the stats of the inter D2D interference and intercell interference. So we call this entire interference, the inter D2D and intercell interference, as IJ. Because we only know the stats of IJ, we can only guarantee we cannot compute the SINR exactly. So we can only compute the estimate. We can only estimate the SINR with a probability guarantee. So we compute an SINR estimate Tij epsilon d such that the actual SINR is more than the SINR estimate with a pre-specified probability 1 minus epsilon d. So if we rearrange this, we get the SINR estimate as shown here, wherein this expression is same as the D2D SINR. In place of this Ij, we now have J inverse of 1 minus epsilon d, where J inverse is the inverse CDF of Ij. So this SINR estimate has this reliability guarantee of epsilon d such that the associated rate corresponding to this SINR estimate has an outage of epsilon d. Once the D2D receiver computes the SINR estimate, it quantizes it and feeds it back to the base station. Once the but note that at the time of feeding back the D2D SINR, the D2D base does not know its co-channel users, because this is happening before the resource allocation. So in that case, how do we get the statistics of IJ? Because IJ is the inter D2D interference of the co-channel users. So how do we know the co-channel users? So in order to compute the SINR estimate, we need the CDF or the inverse CDF of IJ. But how do we know IJ? So one naive thing to consider is that we can consider interference from all the other D2D users, but that would be a very conservative estimate of the inter D2D interference. And moreover, it also points us to think that is it acceptable to let all the D2D pairs to share a subchannel, or we should allow some restriction on the number of D2D pairs that can share a subchannel. So this leads to the cardinality constraint. So in that model, so this addresses a trade-off between spatial reuse and inter-D2D interference. What is that trade-off? So if we let multiple D2D pairs to share a subchannel, yes, the spatial reuse increases. However, it also causes too much of inter-D2D interference. So there is this trade-off between the frequency reuse and the inter-D2D interference. So in order to address this trade-off, we introduce a cardinality constraint wherein at most k D2D pairs can share a subchannel. So if larger the k, higher the spatial reuse, and larger the inter-D2D interference. If smaller the k, lower the spatial reuse, and smaller the inter-D2D interference. So essentially, this parameter k captures the trade-off between the spatial reuse and inter-D2D interference. Now, given the cardinality constraint, the interference, so the ij, the CDF of ij can be computed from k-1 closest to D2D pairs, because we are only allowing k D2D pairs to share a subchannel. Since even now we don't know what the other D2D other co-channel users are, we can conservatively estimate the inter D2D interference from k-1 closest to D2D users. No. So in addition, we also ensure a quality of service guarantee for the cellular users. We guarantee a minimum rate for the cellular users. So if we look at the SINR of the cellular user, so we have inter-cell interference IV, which is random. Only the stats of the inter-cell interference is known to us in the CSI model. So we can only ensure the minimum rate probabilistically. So this minimum rate constraint translates to the following constraint. What it says is that, so in order to ensure a minimum rate for the cellular user, so the cumulative interference from the D2D pairs that share the subchannel with the cellular user cannot be more than a tolerable interference BI. So where this BI is a function of the minimum rate and the probability value epsilon c. So with this, once the D2D pairs feedback the SINR of the D2D pairs to the base station assigns the subchannels to the D2D pairs by honoring the cardinality constraint and also the minimum rate guarantee for the cellular user. So in our model, we focus on the subchannel allocation for the D2D pairs. The subchannel allocation for the cellular users is already assumed to be done. So we have n subchannels and n cellular users, and without loss of generality, we assume that the cellular user 1 is assigned to subchannel 1, cellular user 2 is assigned to subchannel 2, and so on. So the base station, once it has the feedback, it computes it does the resource allocation and then gives the subchannel allocation to the D2D pairs. Sorry?
Capital K is 2 here.
This is just an example. Capital K is not 2. So it is a system parameter that we optimize. So it can be 2, it can be 5, it can be anything. So we will show the results that it varies from CSA model to CSA model. So it is not 2. Yeah. So our goal is to maximize the D2D sum rate by allocating multiple D2D pairs per subchannel while also ensuring the minimum rate for the cellular users. So the subchannel allocation problem is shown mathematically here. So we want to maximize the D2D sum rate summed across all the subchannels and all the D2D pairs subject to the following constraints. So a D2D pair is assigned at most one subchannel, and at most k D2D pairs can share a subchannel. That is the cardinality constraint, and at the cumulative interference cannot be more than a tolerable interference limit to honor the minimum rate guarantee for the cellular user. So here Xij is the binary decision variable that takes either 0 or 1. Because of this binary constraint, this entire subchannel allocation problem becomes NP hard. So to address the subchannel allocation problem, to address the subchannel allocation to D2D pairs, we propose an algorithm based on submodular maximization. So the algorithm is the cardinality constraint subchannel allocation algorithm CCSAA. So in CCSAA, we define a feasible D2D set as the set of D2D pairs that satisfies the interference constraint associated with the minimum rate for cellular users and the cardinality constraint. A set of D2D pairs that satisfy these two constraints is called a feasible D2D set in CCSAA. So what we do in CCSAA is as follows. For each subchannel, we start up with the initial null set, and for each subchannel I, we find a feasible D2D set SI that maximizes some utility function. I'll define the utility function in the next slide. And once the feasible D2D sets are determined for subchannels 1 to n, we then allocate the D2D pairs to maximize the sum throughput. So I will illustrate this with an example. For example, the feasible D2D set for subchannel 1 is D2D1 and D2DJ, and the feasible D2D set for subchannel 2 is only D2D pair J, and for subchannel I is D2DJ and D2DM. So the D2D pairs in the feasible D2D set are assigned to the subchannel. So D2D1 is assigned to subchannel 1, and D2DM is assigned to subchannel I. If a D2D pair is present in multiple feasible sets of different subchannels, then the D2D pair is assigned to the subchannel that has the maximum rate. So among C1J, C2J, Cij, whichever is maximum, the D2D pair is assigned to that subchannel. Now, so how to find the feasible D2D set in CCSAA? So we find the feasible D2D set by solving the cardinality constraint knapsack problem, which is shown here. So the cardinality is the cardinality constraint knapsack problem CCKP is nothing but a feasible D2D set that maximizes this sum of Pij. Here Pij are called incremental gains. So the Pij incremental gain of D2D pair J and subchannel I is nothing but the increment in the rate of D2D pair J for subchannel I over the previous subchannels. For example, D2D pair J has a rate of Cij for subchannel I, and it has a rate of C1J and C2J over the previous subchannels, the subchannels prior to subchannel I. So the increment in the rate of Cij over C1J or C2J is there. If this incremental gain is negative, then we consider zero as the incremental gain. So the objective here is to maximize the incremental gains by respecting the cardinality constraint and the minimum rate constraint. And it turns out that the CCKP is also NP-hard, and we use a half approximation algorithm to find the feasible D2D set to address the to crack the CCKP problem to find the feasible D2D set for each subchannel. Okay, so the interesting thing about CCSAA is that we provide theoretical guarantees about the performance of the algorithm. So the theoretical guarantee is that the sum rate achieved by the CCSAA is at least half of the optimal D2D sum rate when we use 1-bit feedback, and it is at least 1/3 of the optimal D2D sum rate when we use more than 1-bit feedback. And the complexity of CCSAA is CCSAA has polynomial time complexity. It is of the order of n m square log m, where m is the number of subchannels and m is the number of D2D pairs.
Feedback, it's more, it will be more.
No, so when the number of feedbacks is less, in that case, then it gives a very beautiful symmetry. So that is, if there is only one bit feedback, so in that case, the SINR could be either 0 or something else, like one SINR level. In that case, so the guarantee comes because of, so in this case, it turns out this Pij is binary. It can be either 0 or the Pij can be either 0 or Cij. It cannot be anything else, and that makes this entire problem not NP-hard. In that case, it becomes a very special case, and we can solve this problem optimally in that case. That's why the improvement gets better with 1-bit feedback there. If it is more than 1-bit feedback, then Pij can be different. It is non-binary. So in that case, we have to go for the approximation algorithm. We cannot solve that CCKP optimally there. So to summarize these subchannel allocation based on submodular maximization, we proposed practically feasible partial CSI model with low feedback overhead, and we considered cardinality constraint to address the trade-off between the frequency reuse and inter-D2D interference. We proposed the CCSAA, and it provides a theoretical guarantee that its sum rate is at least at 1/3 of the optimal D2D sum rate. Now, we'll move on to the second algorithm that is based on LP relaxation and rounding approach. So here we introduce the second of the two CSI models, which is the statistical CSI model. So in the statistical CSI model, the base station knows, similar to the partial CSI model, it knows the CSI of the CU to base station links and DTX to base station links. However, the DRx the DRx knows the statistics of DTX to DRx, CU to DRx, and the inter-D2D interference and the inter-cell interference. So the difference between the statistical CSI model and the partial CSI model is that in the partial CSI model, we know the instantaneous CSI of this link and this link. Now, even that is not known, only the stats of this link and this link is known. So in this case, we now compute the D2D receiver computes the SINR using the CSI information it has, and it quantizes that and feeds it back to the base station. So to address the subchannel allocation problem that we shown earlier, we propose RPA in this case. So RPA is an adaptation of Smosh and Tardos algorithm. So it has four steps. We relax the binary constraints of the subchannel allocation problem, so which makes it an LP linear program. We solve for that linear program, and then we construct a bipartite graph using the LP solution. From the bipartite graph, we find the maximum matching solution, and then we prune the matching solution to make it feasible. So we'll discuss these steps one by one now. So in step one, so first and foremost, we discard any D2D pair whose interference is more than the tolerable interference. And then we relax the integer constraint to zero between 0 and 1. So this makes the entire subchannel allocation problem into a linear program LP. So wherein the integer constraint is relaxed here. So we solve this LP, let x tilde ij be the optimal solution for this LP. So in step 2, using the LP solution, we construct a bipartite graph. So for each subchannel I, we compute Ni. So as the ceiling of the sum of the LP solution associated with subchannel I. So we create Ni virtual copies of subchannel I. So the virtual copies are I1, I2, so on, INI. So we illustrate the construction of bipartite graph for subchannel I. So first and foremost, we arrange the D2D pairs in the decreasing order of their interference. So the bracketed one is the D2D pair that has the highest interference, and the order D2D2 is has the second highest interference, and so on. I will illustrate the construction with an example. For example, let the LP solution is as follows. Let the LP solution is 0.3 for order D2D1, 0.5 for order D2D2, 0.4, 0.6, 0.3 for 3, 4, and 5. Now we start with a virtual copy of I1, and then we consider 0.3 from order D2D1, and we consider 0.5 from order D2D2. We only take 0.2 out of 0.4 from order D2D3, so that the sum of the LP solution is 1 here. So we then construct the adjust between virtual copy I1 and order D2Ds 1, 2, and 3. Now, so we'll move on to the virtual copy I2, wherein we take the remaining part of 0.2 from order D2D3, and we take 0.6 from order D2D4, and we take 0.2 from order D2D5, such that the sum of the LP solution is 1. So the edges are created from virtual copy I2 to D2D base 3, 4, and 5. So likewise, we construct the bipartite graph between the virtual copies of subchannel and the D2D pair. Note that this 0.3, these fraction values are not the weights of these edges. The weights of the edges are the rate of the D2D pair for that subchannel, for subchannel I. For example, the weight of this edge is the rate of the order D2D2 on subchannel I. That is the weight of the edge. Now, so we construct the bipartite graph. We repeat that procedure for all the subchannels, and we construct a bipartite graph, the complete bipartite graph with virtual copies of all the subchannels on one side and the D2D pairs on the other side. Now, on this bipartite graph, we apply Kunmungre's algorithm to find the maximum matching solution. This matching solution is such that we want to maximize the sum rate of the assignment. Okay, I will illustrate what that is. So the matching solution is such that a virtual copy can only be assigned to one D2D pair, and a D2D pair can only be assigned to one subchannel. So this assignment is considered such that the sum rate is maximized. Now, so in the bipartite graph, in the matching solution, we say that D2D pairs assigned to virtual copies of any subchannel are assigned to that subchannel. For example, D2D pairs 1 and 3 are assigned to the virtual copies of subchannel N. So we say that 1 and 2 are assigned to subchannel N. Similarly, D2D pairs 2 and M are assigned to subchannel 1. So note that the D2D here we did not consider. So during the matching, we did not consider the interference constraint into account. Interference constraint associated with the minimum rate of the cellular usage. So this matching solution may not satisfy the interference constraint at all. No, may or may not satisfy the interference constraint. For example, for some subchannels, if it does not satisfy, then we prune the matching solution to make it feasible. For example, let subchannel I be the matching. Subchannel I has a matching solution that does not satisfy the interference constraint. In that case, let's say the matching solution is as follows. For virtual copy I1, D2D pair K1 is there, I2, K2, INI, KNI is there. In that case, if the rate of D2D pair K1, if it is more than the sum of the rates of D2D pairs K2 to KNI, then we assign D2D pair K1 to subchannel I. Otherwise, we assign D2D pairs K2 to KNI to subchannel I. And we show that this assignment is actually feasible. And so we prune all the matching solution that does not satisfy the interference constraint, and that gives us the final feasible allocation of the D2D pairs to subchannels. Now, like CCSAA, so we also show that RPA also provides theoretical guarantee about its performance. The performance guarantee is that the sum rate achieved by RPA is at least half of the optimal D2D sum rate when the D2D assignment limit is this K is the parameter associated with the cardinality constraint, the D2D assignment limit. When it is more than 1, we achieve half of the optimal D2D sum rate. When K equal to 1, it achieves optimal D2D sum rate. This again boils down to that special case when K equal to 1, the problem becomes much more easy to solve problem. And it has polynomial time complexity in the number of D2D pairs, and in the number of the complexity of PA is order of n cube m cube, where n is the number of D2D pairs and m is the number of subchannels. So we now look at the statistical rate upgradation technique, which is applied after subchannel allocation to improve the D2D sum rate. So remember that before the resource allocation, we computed the SINR estimate Tij epsilon d. The DRx, the D2D receiver computes the Tij epsilon d by considering interference from the K-1 closest to D2D pairs. But after subchannel allocation, the base station transmits broadcasts the subchannel allocation information to the D2D pairs. Now the D2D pairs knows who are its actual co-channel users. So the D2D pair now can estimate its SINR estimate by using the statistics of its actual co-channel users instead of the K-1 closest users. So this new SINR estimate will always be more than the SINR estimate PH epsilon D that is completed before the subchannel allocation. So now the D2D pair can upgrade its rate from CIJ to the rate associated with the new SINR estimate. Okay, so we observe an interesting interplay between the two CSI models and the two algorithms that we proposed. Here we show figures for partial CSI model. The one on the left hand side is partial CSI model. The one on the right hand side is statistical CSI model. So in the two figures, we plot D2D sum throughput as a function of the D2D assignment limit, the parameter K associated with the cardinality constraint. So we show RPA in blue and CCSAA in red. And we show it for different feedback resolution bits, Q equal to 1-bit feedback, 2-bit feedback, 4-bit feedback, and full feedback. First and foremost, we see, so the values are not visible here. The D2D sum rates in the partial CSI model are significantly higher than the rates in the statistical CSI model. This is because of the better CSI information the partial CSI has. And if you look at the performance of RPA and CCSAA in the partial CSI model, RPA performs better than CCSAA in the partial CSI model, whereas CCSAA in red performs better than RPA in blue in the statistical CSI model. And so if you see it for larger K values, the performance of RPA and CCSAA are the same in partial CSI model, whereas the performance difference is clearly visible for large K values in the statistical CSI model. And moreover, it seems that as K is increasing, the D2D sum rate is increasing and then saturating here, whereas the D2D sum rate is increasing and then decreasing with K in the statistical CSI model. But in fact, if you see it closer enough, it is not saturating, it is decreasing with K. The D2D sum rate increases and it decreases with K. That is clearly visible for 1-bit feedback. For higher resolution feedback, it is not clearly visible. Moreover, so this is because the visibility of the decrease in the rate with K is because the effect of inter-D2D interference is more in the statistical CSI model than in the partial CSI model. That's why we are able to see this difference here, but that is not so significant in the partial CSI model. So we also compare here we show the scalability of the RPA and CCSAA as with the number of D2D pairs. So here again we plot the partial CSI model on the left hand side and statistical CSI model on the right hand side. We plot D2D sum throughput as a function of the number of D2D pairs in both the figures. So moreover, these figures also highlight the importance of SRU. So the SRU, if you look at the rates here compared to the previous slide, the rates are of the order of 7, maximum 8 here, but here the rates increases. So this is because of this is the effect of SRU. The SRU significantly improves the D2D sum rates in both the cases. And moreover, if we see it increases as the feedback resolution Q increases and M increases, the D2D sum rate increases in both the RPA and CCSA and in both the CSA models. So we benchmark RPA and CCSA with SSA, the SSA called semi-orthogonal sharing assignment algorithm, in which at most one D2D pair is assigned per subchannel. SSA uses Kuhn-Munkres algorithm and it finds the optimal allocation. However, so this shows that the assigning multiple D2D pairs per subchannel in fact improves the system performance than assigning only one D2D pair per subchannel. And we see that as the number of D2D pairs increases, the performance throughput also increases. Now, to summarize, so we propose the second of the CSI model, which is the statistical CSI model and RPA. And RPA provides at least half of the optimal D2D sum rate. And we have seen an interesting interplay between the two algorithms and the CSI models. So the interplay is as follows. So the RPA and CCSAA, so they respond differently to the partial and statistical CSI models. So RPA performs better in the partial CSI model and CCSAA performs better than RPA in the statistical CSI model. And we see that the effect of inter-D2D interference is more in the statistical CSI model than the partial CSI model. And moreover, I forgot to mention that the optimal value of K is actually different in both the CSI models. For example, optimal value of K here in this case, maybe it is 3 here and it is 2 here. And for example, it also changes with the feedback resolution. It is 2 here. So it changes depending on the CSI model, depending on the, for example, in the CCSA case, the optimal value could be, say, maybe 6. So the optimal value of K depends on the algorithm and the CSI model and the feedback resolution. And also, it also depends on the number of D2D pairs and subchannels that are employed. So if we change the number of D2D pairs and subchannels, we'll have a different optimal value of K there. Okay, so we now move to the subchannel allocation based on disjunctivity constraint. So in the previous subchannel allocation, we have seen the inter-D2D interference. The SINR estimate is computed by considering the inter-D2D interference from K-1 closest to D2D pairs. And so if we have dense D2D networks where the D2D users are very closely spaced, and the interference from the closest to D2D pairs can be excessive. It can be too much inter-D2D interference. So in that case, so we should have a disjunctivity constraint. So what is this disjunctivity constraint? So in disjunctivity constraint, two D2D pairs cannot share a subchannel if they cause significant interference to one another. So for example, if these two D2D pairs, they cause significant interference to one another, they cannot share a subchannel. So what is significant interference depends on the definition that we assign to the significant interference. So the disjunctivity constraint can be based on the path loss and it can be based on the fading average interference. For example, so we say two D2D pairs cannot share a subchannel if they are within certain distance. If they are above that distance, the two D2D pairs can share a subchannel. So like we have seen in the earlier case, the two D2D. So here in this case, this is one way of looking at it. So if the two D2D pairs are significantly close, if they are within a certain distance, they cannot share a subchannel. But if they are far apart, they can share a subchannel. So this is based on the distance. So we can also use the disjunctivity constraint by considering the fading average interference, which means it considers the path loss and shadowing while measuring the significant interference. For example, if the fading average interference between the two D2D pairs, if it is more than certain threshold, then they cannot share a subchannel. If it is less than certain threshold, then they can share a subchannel. So that is the so the disjunctivity constraint can be based on the path loss and the fading average interference. Now, so we incorporate the disjunctivity constraint into the subchannel allocation problem. We want to maximize the D2D sum rate while also ensuring the minimum rate guarantee for the cellular user, the interference constraint, and also honoring the disjunctivity constraints. So two D2D pairs, if they are disjunctive, that means if they are causing significant interference to one another, they cannot share a subchannel. And so note that in this problem, this interference constraint is specific to each subchannel, and this disjunctivity constraint is applied for every subchannel. And there is no binding constraint for a D2D pair across the subchannel. That means there is no limit on the number of subchannels a D2D pair can use. Here, a D2D pair can transmit on multiple subchannels. So in this case, because there is no, so the D2D assignment is independent across the subchannels, we can solve the D2D assignment individually for each subchannels. So for each subchannel, we solve the D2D assignment by solving this problem. So this is known to be disjunctivity constraint Knapsack problem, DCKP problem. So this is again the same problem, but specific to a subchannel. So we want to maximize the sum rate subject to the interference constraint and the disjunctivity constraint. And this problem is also known to be NP hard. So to address this problem, we propose a branch and bound algorithm. So in branch and bound algorithm, we find the optimal solution by constructing a bipartite graph. So in the bipartite, by constructing a binary tree. In the binary tree, for example, x1 denotes the for D2D pair 1. So if x1 equal to 0, D2D pair 1 is not considered. If x1 equal to 1, D2D pair 1 is considered. And we keep on constructing branches until all the D2D pairs are considered. So this binary tree, so we can find the optimal solution by doing exhaustive search across the binary tree. So, however, this is computationally expensive. So we can reduce the set space of this binary tree by using the bounds of the DCKP problem, bounds on the sum rate of the DCKP. So we derive lower and upper bounds on the D2D sum rate. We derive the lower bound so we propose greedy algorithm to determine the lower bound of the DCKP, and we also find the upper bound by using Lagrangian based NP relaxation. So we use these bounds to reduce the set space. So we reduce the set space by pruning a node. So pruning a node means that we stop the node branching out further. So if any of the following conditions are satisfied, for example, so we prune a node if at any node, if the upper bound is less than the lower bound that is already determined, then we prune that node. So the upper bound at a given node means that, for example, in this case, x1 and x2 are already decided to be 0. Now, from here onwards, whatever is the upper bound, that upper bound cannot be, if it is less than the lower bound that is already known, then going forward from this node is of no use because it is not going to give us the optimal solution. Now, we also prune a node if it does not satisfy the disjunctivity constraint. What it means is that, for example, at this node, here the D2D pairs 1 and 2 are selected, and if the two D2D pairs are disjunctive, if they cannot share a subchannel, so there's no point going further from this node. So we prune that node if the constraint is not satisfied. Similarly, so we prune the node if the interference constraint is not satisfied. So again, if the sum of the interference at a node traversing along the path, if the interference is more than the tolerable interference, there is no point going further. So we prune this node. We also prune the node if one node dominates the other node. For example, so in this case, let's take this path where x2 is selected, and let's take this path, the one in the magenta, where x1 is selected. So if the interference of this path is less than the interference of this path, and if the rate of this path is more than the rate of this path, and if the set of D2D pairs that are not feasible with this path, so in this case, the set of D2D pairs that are not feasible with D2D pair 2, so if it is a subset of the set of D2D pairs that are not feasible with the D2D pair 1, the one corresponding to this path, then we say that this node is dominated by this node. So in that case, we prune the node that is was dominated. So there's no point going further because going along this path will always give better solution than this node. So so among these, so we saw that as among these pruning conditions, the one in the first, the upper bound. So the pruning using the upper bound. So when the upper bound is less than the lower bound, kind of reduces the set space more compared to the other constraints there. Here we show the results for the DCKP subchannel allocation problem. Here we plot D2D sum rate as a function of the interference threshold. This interference threshold, so this is the threshold that we use to determine the disjunctivity constraint. If the interference between the two D2D pairs, if it is more than the interference threshold, then they cannot share a subchannel. So here we show it for different cases. The one in the solid blue is the case where the interference between the D2D pairs is considered using path loss and shadowing. The one in the red, the dotted red line is the one where we determine where the inter-D2D interference is considered based on distance. So we see that considering the shadowing, accounting for shadowing while considering the disjunctivity constraint, and also we have other things that are specific to the model. So accounting for shadowing in both the disjunctivity constraint and the SINR computation improves the system performance better than considering only the path loss. But also we see that the optimal value of the inter-D2D, the interference threshold actually varies from how we measure the inter-D2D interference, like whether we want to consider the path loss or the fading average interference. Now, so I want to highlight the importance of DCKP by this figure. So this figure is the one where we restrict the D2D pair to share only one subchannel. So in this case, we can compare the disjunctivity constraint algorithms, disjunctivity constraint approach with the RPA and CCSAA algorithms that are considered earlier. So here we plot D2D sum rate as a function of the number of D2D pairs M. We see that the blue line is the one that considers the disjunctivity constraint based on fading average interference. The red line is the one that considers disjunctivity constraint based on the path loss. The dashed blue line is RPA, the dashed red line is CCSAA, and the dashed green line is SSA. So as the number of D2D pairs increases, the D2D sum throughput in all these cases increases, but we see that the disjunctivity constraint approach significantly outperforms the RPA, CCSAA, and SSA. And it clearly highlights the importance of the disjunctivity constraint in dense D2D networks. And it also outperforms the RPA and CCSA and SSA significantly. With that, so I will summarize the disjunctivity constraint based subchannel allocation. So disjunctivity constraint is critical for dense D2D networks, and it avoids the conservative estimate of the inter-D2D interference, and a proposed branch and bound. So we propose branch and bound algorithm in this case, and the disjunctivity constraint effectively manages the inter-D2D interference and achieves the higher system throughput. So accounting for sharding actually improves the system performance. Now, to summarize, so we looked at, we saw that for resource allocation, CSI acquisition is critical and challenging for underlay D2D networks. And we proposed two practically feasible CSI models, partial and statistical CSI models that has low feedback overhead. We proposed polynomial time subchannel allocation algorithms, and we looked at the trade-off between the spatial reuse and inter-D2D interference by introducing the cardinality constraint. And we investigated the interplay between the two CSI models and the algorithms. And the performance of these algorithms varies with the two CSI models. And we also see the disjunctivity constraint is extremely critical for resource allocation and dense D2D networks to manage the inter-D2D interference. So these are the publications that came out of this work. The first journal is based on the submodular maximization based subchannel allocation. It has more algorithms other than CCSAA. It has two more algorithms, and it has more results, and it has the proof for the theoretical guarantee. The second journal is based on the LP relaxation and rounding approach, the RP algorithm, and the statistical CSI model. And it also discusses the interplay between the CSI models and the algorithms in more detail, and it provides more insights into it. And it also gives the theoretical guarantee of the RPA. And in the third journal, we look at the disjunctivity constraint based subchannel allocation. We are to submit this one, and the two conferences are the part of the first journal and the second journal. Thank you.
Questions online or